Okay, great. Okay, yeah, so thank you very much. Thanks for inviting me to present your seminar series. I'm just going to share my screen. Okay, great. Yeah, so I'll get started. So I'm a professor at the University of Western Ontario. I've been here for 12 years. Before, just to give you some background, before I started at Western, I worked as a water supply and sanitation engineer in Bangladesh for 12 months. And so when I came to Western, it was originally to support the Civil Engineering and International Development program that we have here. So I teach courses in that area. And I also continue to do some research around kind of the WASH theme as well, amongst other themes, kind of more specific to the Canadian context. Yeah, again, thanks for joining. Before I get started, flip slides. I'd just like to provide a land acknowledgement that I acknowledge that where I am at Western University is on the traditional territories of the Anishinaabe, Haudenosaunee, Lenape, and Chinootan nations, and that this home is diverse to Indigenous people whom we recognise as contemporary stewards of the land and vital contributors to our society. So with that, today in my presentation, I'm just going to talk about two different projects that I've worked on related to groundwater resource challenges, one related to drinking water supply and the other one related to ecosystem protection in two very different developing contexts. So as I'm sure many of you are aware, groundwater is really a very important water supply source in many areas or for many communities around the world, both for drinking water as well as for irrigation. And so it's estimated that groundwater supplies approximately 50% of drinking water globally. And in some areas, it's really the only accessible and reliable source of fresh water. One of the main benefits of using groundwater is that when it is accessible, it is generally available year-round, so it can be a very reliable source of water. But in addition to that, groundwater typically has very low microbial contamination. Because the kind of aquifer sediments themselves provide natural filtering, it means that groundwater generally has low pathogen concentrations, so low levels of viruses, bacteria, that can lead to kind of acute diarrheal diseases, cholera, and those sort of public health challenges. And so that's why in a lot of areas they kind of promote the use of groundwater to provide a safe, improved drinking water option. One of the main disadvantages of groundwater, however, is that in some areas it can be contaminated, including naturally contaminated. So in coastal areas, you can get high levels of salt concentrations in the groundwater because you've got intrusion of seawater into the groundwater system. And then in other areas of the world, you can have high levels of metals such as arsenic, fluoride, iron, manganese. And these can be high just because of the natural geology and geochemistry within the aquifer systems. And these high levels of metals can be problematic. One, because, they might just cause, in the case of iron, they might cause a discoloration of the water, which means that people don't want to drink the water. But, for the cases such as arsenic and fluoride, they can lead to severe chronic health impacts. So in my talk today, as I said, I know this is more of a multidisciplinary audience. So rather than just focusing on the details of one specific problem, I wanted to just talk about two different projects I've worked on over the years. One is a project I worked on, quite a number of years ago that was focused on in Bangladesh, related to water supply. And the other project is a more recent project that's currently ongoing, which is in the Pacific nation of Tuvalu. So just to start with Bangladesh. So for those of you who aren't familiar with Bangladesh, it's just to the east of India, and it actually has India that kind of wraps around its borders. So Bangladesh is one of the most, it's a small country, but it's one of the most highly densely populated regions in the world. It's got a population, I think, around 4 or 5 times the size of Canada, that's nestled into an area the size of southern Ontario. So a very dense population. But in addition to that, it's very vulnerable. It's got a kind of the whole suite of water and sanitation challenges across the country. So it's a very low-lying delta. So there's a lot of major rivers that kind of come down through the Himalayas, through India, that come down through the delta system that is Bangladesh. So I think around 90% of the country is within 10 meters of sea level, meaning that it's very vulnerable to climate change effects, such as sea level rise. You get hurricanes that come up every few years through the Bay of Bengal, and impact the coastal communities, as well as you get severe kind of monsoon flooding throughout the country as well. In addition to this, because a lot of the major rivers that come through Bangladesh originate in very densely populated areas, including in India, you have very highly contaminated surface water. And then kind of compounded on top of this, what I'm going to talk about today is that they also have, contaminated groundwater as well. So this is just some photos to give you a little bit of a snapshot of the context of Bangladesh. This is more from the surface water side of things. So this is a photo that's taken on the major river that runs through Dhaka, the capital of Bangladesh. And you can see in this photo that the how maybe not clean the surface water is. So you've got this, it looks black, and that is because it is. In the dry season, you've got very highly polluted surface water because of, like poor wastewater treatment facilities and solid waste management upstream. Of this area here, you've also got a lot of industry and tanneries. So a real challenge to be able to use this surface water for either irrigation or drinking water supply. And then this is just an image of, just looking at the solid waste disposal into the surface water bodies, as well as poor kind of sanitation facilities. Where here you've got a hanging latrine and you've got raw wastewater being kind of disposed straight into the surface water bodies. And so these are kind of common images that you'd see around surface water bodies in Bangladesh. So today I want to talk in particular about the arsenic contamination of groundwater in Bangladesh and the challenges and some of the solutions associated with this issue. So to provide a bit of background to the arsenic contamination challenges in Bangladesh, because I think it's kind of an interesting point, is that before the 1970s, surface water was really the main drinking water source for the rural populations across Bangladesh. But because these surface waters are really contaminated, they had very high levels of infant mortality, high prevalence of diarrheal diseases, including cholera. And so from the 1970s onward, there was a really large, from international organizations, supported by national organizations as well, to try and switch or change the habit of people, to switch people to using groundwater, because it's typically pathogen free and it's not associated with those kind of acute diarrheal diseases. And in this context, Bangladesh and the NGOs working on this really achieved remarkable success in terms of, and by the end of the 1990s, nearly 100% of the population in Bangladesh was using groundwater from the shallow aquifer systems. However, in the late 1990s, it actually became apparent that the shallow groundwater, or the tube wells that were being used by all the communities, actually had very high levels of arsenic in the water, and considerably higher than the World Health Organization standards. And so this, of course, is a major challenge, because, as I'll show you in the next slide, arsenic in drinking water is associated with a lot of chronic health impacts. And so it first became apparent that there was arsenic contamination in the groundwater because they were starting to get a really high prevalence of health issues, such as a lot of people coming forward with cancers or respiratory illnesses or skin lesions. And then they linked this to the water supply having these high arsenic levels. And the high arsenic is naturally occurring, as what I'll talk about in the next slides. So despite, it being known now for nearly 30 years that you have high arsenic concentrations in the groundwater in many rural areas across Bangladesh, there's still, it's estimated, this is from 2011, but, there's still, many millions of people that are still drinking arsenic concentrations above the World Health Organization standards. And it remains a real challenge still to develop sustainable water supply options for communities that have a high uptake and are sustainable in the long term, despite, over the last 30 years, billions of dollars being invested to provide alternative water supply options to communities. So just, step back just to show you, there's a lot of long-term health effects associated with arsenic. As I said, whether it's respiratory illnesses, cardiovascular illness, cancers, skin lesions. These skin lesions can then lead to social problems where, if you have a daughter who develops skin lesions, it can then be difficult for them to marry off. So you've got kind of a whole suite of health impacts associated with the arsenic contamination of the groundwater. One of the real challenges, however, with trying to implement sustainable long-term alternative safe drinking water options in Bangladesh is that because it's a chronic health effect, it's really hard for people to link what their kind of long-term health impact, they have a cancer, with the fact that that's because of the arsenic contamination. It's much easier to get a direct link between, okay, I drank this water from this polluted surface water body yesterday, and that caused me to have diarrhea today. People can normally see the causes and effect. But with these groundwater contaminations, such as arsenic and fluoride, it can be often more challenging to kind of implement solutions and get community uptake because people don't appreciate that direct link. So also I just want to note before I kind of move further on that while the work that we did, and my talk here is more focused on Bangladesh and the high concentrations of arsenic in the water supply in Bangladesh, this is also a challenge in other countries in the world, including in the Mekong Delta, so in like Laos and Cambodia, as well as some areas of China and in South America as well. And so it's estimated there's around, over between 100 to 200 million people who are drinking domestic water supply with high levels of arsenic. So in terms of kind of the situation in Bangladesh, people tend to drink, a lot of the population drinks out of these shallow groundwater wells, which they refer to as tube wells, that are installed, and these tube wells have been installed in the shallow aquifer. Now, as I mentioned before, Bangladesh is a delta, and what that means is over the landscape, you've had the deposition of kind of fine sediments that have come down the rivers. And so as a result, the kind of shallow kind of aquifer system or geology is generally kind of very fine, reduced sediments. And it's in this area that you have, in these shallow aquifer, you tend to have these very high arsenic concentrations that are much, much higher than the Bangladesh standards, as well as the World Health Organization standards for arsenic. And so this is just naturally occurring, that the sediments that are coming down these rivers that originate from the Himalayas have kind of levels of arsenic associated with them that then get reduced and that then get released under these reducing conditions in the aquifer. In the lower aquifer, however, the sediments are generally more oxidized, and when you have more oxidized sediments, you tend to have more metal oxides, such as iron oxides, and in this particular, and then these iron oxides sequester the arsenic into the solid phase, so you end up with very low arsenic concentrations in the groundwater. So they tend to refer to these areas with the reduced sediments as arsenic unsafe, and in the lower oxidized sediments is kind of arsenic safe groundwater. So the reason, however, tube wells are generally installed in this shallower environment is because it's cheaper, and there's very simple local drilling techniques that can be used to install shallow tube wells or groundwater wells and be able to pump out this groundwater from the kind of shallow aquifer system. And so all through villages in Bangladesh, you'll see, tube wells everywhere because they're really quite easy and cheap to install using local methods. But obviously a lot of these wells have high arsenic concentrations. So there's lots of different options for providing arsenic safe water. So there's two different ways you can go. One way is you can use the same source of water, so continue using the same tube well, but instead use like an arsenic removal system, such as a membrane filtration system that might be at the household level, or you use a filtration system that's installed onto the groundwater wellhead. And then the other option is just switching the water source, so trying to get the community to switch water source to a low arsenic water source. So that might be, for instance, back in around the 2000s, they went through and did like mass testing of shallow tube wells throughout the country. And in doing that, when a tube well had high concentrations, they painted it red. When it had low concentrations, they painted it green, as you can see here. So trying to get people to use the wells that were arsenic safe and they were green. But there's kind of long-term challenges associated with that approach. The other options are getting people to use rainwater. That is a really good source of water, but it can be problematic in many areas because they get seasonal water scarcity. You have pond sand filters, which is more of a community-based system, as well as deeper groundwater wells as well. And so by using the deeper that's not spelled right, but the deeper groundwater wells is you're tapping into that arsenic safe zone where the sediments are more oxidized. So the deep groundwater wells is really one of the ones that has the highest uptake, as I'll show you in a couple of slides. And that is because it doesn't require the community to switch habits. They already have the habit of going to a tube well to water. And so by just having a tube well, but it being tapping into deeper aquifer system is kind of a good sustainable option with high community uptake. But the challenge with these deep groundwater wells is that when you have to install these deep groundwater wells, you can no longer use kind of the cheap, low technology drilling techniques, but instead it's very expensive. And you've got to be bringing in skilled workers. You've got to be bringing in very sophisticated drill rigs to put in these tube wells that can kind of tap deep into the aquifer, into this kind of arsenic safe aquifer zone. So, and while there's been billions of dollars that have been provided to Bangladesh to install different, safe water interventions, including deep tube wells, so there has been money that's been available to do this. One of the real challenges is that there have been a lot of deep tube wells installed, but where they've been installed is not necessarily always targeting the most vulnerable populations, but instead where they're installed is often politically motivated. And so it's given to like political allies or their supporters, or it's given to, the richest person in the village, and then they don't necessarily share access to that tube well with the rest of the community. So there's a lot of political issues with the installation of these deeper tube wells, which are more expensive. So this is kind of some results from the study that I was first involved with. And this was in an area of Matlab, Upazila, a community area where they had really high arsenic concentrations in the groundwater, and it's a rural community. And what they did here was there was a lot of different safe drinking water interventions that were provided to different households throughout the kind of the district. And they came back 3 years later to look at what the uptake was of these different interventions. So whether it was a arsenic safe tube well, a rainwater harvesting system, a pond sand filter, or different filtration units. And this is really kind of says it all in terms of that you can see how high this is after 3 years, you can see how high the abandonment of a lot of these interventions are. And the reasons for these interventions are things like the water smelled bad, it was dirty, you know, it wasn't maintained properly, things started breaking, things were stolen. So and the only kind of intervention that really had high uptake was the supply of was kind of the arsenic safe tube wells. And so this really kind of highlights that it's not that there aren't, you know, a lot of technology available that can provide safe drinking water interventions, and that can be provided. But it's more that, you know, there's just not the long-term uptake and community acceptance of these kind of different interventions. And so kind of showing that you know, often the technical engineering design is really only one piece of the solution, but you do need all that capacity building, education, ensuring that there's kind of a long-term maintenance process in place to ensure that a water, you know, supply intervention is going to be sustainable in the long term. So the reason why, as I said, these arsenic safe tube wells have low abandonment is they don't require a switch of habit. People are used to doing that. It's easy for people to do. You know, and they understand the maintenance and how to use it. So the particular project that I was involved in here was looking at, so in a lot of the hydrogeology in the shallow aquifer, although there is a lot of areas where the sediment is reducing and you've got these very, you know, arsenic unsafe or high levels of arsenic in the groundwater, there are areas where you do get at a local scale, you know, like you get kind of more oxidized shallow sediments where the groundwater is actually safe. And so the hypothesis for the project I was working with some researchers from KTH in Sweden, was the hypothesis that if local drillers, are able to look at the sediment color as they're installing their shallow tube wells, they should be able to, that if they can see that the sediments were kind of reddish or brownish, this would mean that these sediments would have high probability that the groundwater extracted from the tube well would be arsenic safe. So this kind of works on the thought that when you have reddish brownish sediments, you've got a lot of iron oxide minerals. That's what gives the sediment its color, and the arsenic absorbs onto these iron oxide minerals, and so therefore the groundwater is safe. So the first thing that we had to do here was to do the science and look to see whether, okay, are the arsenic concentrations lower when the sediment is reddish brownish? So we had to develop kind of a sediment color scheme that the drillers could use to identify what the sediment was as they were drilling their shallow tube wells. And then, so this is what's on the left here. So we had different classifications of white, off-white, red, and black. And then on the right-hand side, you can see these are kind of results of what the arsenic concentrations are for different kind of sediment colors. So you can see that when you have black sediment, which is, you know, grayish or these kind of in this range, you tend to have, you know, very high arsenic levels above the Bangladesh and the World Health Organization standards. But you do get off-white and white in the shallow aquifer that actually have low arsenic concentrations. So it works on the premise that if drillers are able to identify the sediment color, and if in the shallow aquifer they see these white and off-white sediment layers, this is then maybe a suitable area for them to install the tube well, which will then be able to provide arsenic safe drinking water to the community. So this was kind of the science part of it. And then the other part of it was kind of, which I wasn't as involved with, but the kind of national and local NGOs were working very extensively with the driller to train them in how to use these color charts to better identify the sediments were white or off-white, and then they could target them for drilling installation, and also working with the community so that they knew that which are the specific arsenic safe tube wells that they should be targeting. So with that, I'm going to finish that area, and I'm going to talk about the second project that I worked on, and this is kind of a recent project that's ongoing. And in this particular project is focused in Tuvalu, which is a Pacific nation, and it's an atoll island nation. So for those of you who aren't familiar with atoll islands, there's about 400 of these islands in the Indian and Pacific Oceans, and they typically have kind of a distinct circular population, circular formation. And in a lot of areas, in a lot of atoll islands, you can have very high populations living in a very narrow strip of land. According to the IPCC, these are one of the most they're in the highest risk category for climate change impacts, such as sea level rise, flooding, availability of freshwater supply, and these kind of physical vulnerabilities compounded by socioeconomic constraints, such as, low socioeconomic populations living in very remote areas. The population densities in these islands can reach up to 12,000 people per square kilometre. So you can contrast that to British Columbia, where it's around 5 people per square kilometre. So very, very dense populations. So with dense populations and these climate change challenges, you get water supply and sanitation issues as well. So in these very remote atoll island environments, there's limited freshwater supply. And so, they'll use rainwater, but rainwater can be either seasonally scarce or it can be scarce from year to year because they have a strong El Nino where at a longer lot of rain, and other years they kind of go through drought conditions. And so one of the most reliable sources of fresh water in these atoll environments is the fresh groundwater lens. So you get as it rains, you get recharge into the groundwater system, and you get a kind of a shallow groundwater lens that forms. And so in a lot of these atoll islands, they have infiltration galleries that are set up to be able to kind of skim off the fresh groundwater from the top of the aquifer system. But despite this, a lot of these islands are suffering major water security challenges because of these rapidly growing populations compounded by climate variability and climate change effects as well. So today, though, I'm not going to talk about water supply on these issues, but I want to talk more about one of the ecosystem threats, and that's eutrophication of the atoll lagoons. So you've got dense populations, they generate a lot of nutrients, for instance, in the wastewater or from, the animal husbandry that they might do. And so a lot of these atoll island lagoons are suffering from eutrophication or leading to algal blooms, in some cases hypoxic dead zones. And this is a major issue because these atoll lagoons are really important fisheries. And so they're very important for sustaining the livelihoods of the people who live on these atoll islands. And they're a really important source of income as well, because in some cases they'll sell fishing rights to international fishing boats to be able to fish in their waters. So it's also an important source of income as well for the communities. So the work that we're doing is trying to understand how important groundwater might be in delivering nutrients into these atoll lagoons. And our specific study site was in Tuvalu, which is located in the Pacific Ocean, midway between Australia and the Pacific. It's got a population of around 10,000 people in an area which is, less than, most of the population lives in an area less than, let's say, 5 kilometres squared. So a very kind of dense population in a small area. And the maximum elevation across this area is only 5 metres above sea level, with a lot of the island only 2.5 metres above sea level. So it's very vulnerable to storm surges. They get a lot of inland flooding as the groundwater table rises So the reason why we were working here was that they have increasing macroalgal blooms in the lagoon, which is linked to high nitrate concentrations. And this is kind of causing impacts for their fisheries and for their livelihoods. So one of the major sources of nitrogen to the lagoons is likely the human wastewater. And so across the Whangawhali Inlet, they use septic systems for the treatment and the dispersal of wastewater. But many of these systems are not functioning well. Either they weren't properly installed or they haven't been properly maintained. And so as an example, in Ontario and British Columbia for a septic system, you need to have a certain distance between the septic drainage field, so where the wastewater is dispersed, to the water table. But in these atoll environments, often the water table is very close to the surface. So they don't have this kind of vertical separation distance, which is where you get a lot of the removal of the contaminants below the septic system. And so the work that we were doing, it was trying to look at, was firstly trying to understand how important these septic systems might be in delivering nutrients into the coastal lagoon, and just getting some understanding of what are the like if you get nutrients into the aquifer system, what kind of timescale does it take for them to go from the septic system into the lagoon? What kind of dilution occurs? And so that we could better kind of inform field investigations and some of the like wastewater infrastructure upgrades. So the overall study objective was to kind of evaluate the groundwater pathways for the nitrogen from the septic systems to reach the atoll lagoon, including, the influence of tides, interannual variable recharge, as well as septic system locations. And so this work was done in collaboration with the Pacific community, which is kind of one of the large NGOs that work in the Pacific under a large project, coastal aquifer management project that they have. And so the findings from this work were used to inform field investigations, as well as to guide wastewater infrastructure upgrades. So originally at the inception of the study, we had plans that we'd be doing field work there, but because of COVID, this kind of more turned into a numerical modeling investigation, and the field work it's going to help inform the field work that will occur. So for the work that we did, we developed a numerical groundwater flow and transport model across a kind of island transect from the lagoon into the ocean. And so this is kind of across an area that's very densely populated and across an area where there's some idea about what the hydrogeology is. So in atoll islands, they have very distinct hydrogeology, which is different to kind of mainland systems where they have lower permeability aquifer or Holocene deposits in the upper aquifer, and then typically because of the kind of the way these atoll islands are formed, they get lower kind of high permeability kind of limestone sediments further below, and this means you get very distinct groundwater pathways for contaminants such as nutrients compared to in like a mainland aquifer system. So I'm not going to go into the details of the model, but overall it was just kind of a two-dimensional slice where we had the lagoon on one side, the ocean on one side. We were considering the kind of the distinct hydrogeology of the island and atoll islands with lower permeability upper sediments, high permeability lower sediments. We considered tides, we considered variable recharge and how that would change kind of the nutrients moving through the system. We also ran simulations where we had a single septic system located at different locations across that island transect. And we also ran simulations where we looked at where the households were located along the transect and ran simulations where we had multiple septic systems. So if we, and then we had to make assumptions on what that household wastewater loading was and what nitrogen was associated with that wastewater loading. So if we just look at some of the kind of results, here you can see, so in red, this is kind of a nitrogen plume moving from a septic system that's 120 meters inland from the lagoon. And you can see it kind of moving downwards and it discharges off into the lagoon. So for all cases that the septic discharge, because a lot of the population's on the lagoon side, it discharges into the lagoon rather than into the ocean. And that's important because that's what the lagoon is more sheltered, and so you don't get as much offshore ocean circulations that can kind of move the nitrogen offshore, but instead you get these eutrophic conditions that develop in the lagoon. We see that, the travel times from a household that's about 120 meters inland is about 5 years. This is important because it means that even if they implement wastewater they change the wastewater infrastructure practices now, there's a legacy issue where it's going to take time for this problem to be resolved because the nitrogen, it moves very slowly along these groundwater travel pathways. And we see, some dilution of the nitrogen in the system as well. When we consider tides, we get more dispersion or mixing of the septic of these nutrient plumes or nitrogen plumes in the aquifer. You're getting slightly longer travel times. The exit concentration kind of decreases because you're getting a lot more dilution occurring in the aquifer system. And then we also looked at kind of variable recharge and when it changes from year to year. And surprisingly, that didn't have a major influence on the kind of the behavior of the nitrate in the nutrients, nitrogen in the groundwater system. If we just look at a summary of the results of when we had individual septic systems located at different distances from the shoreline, we see that as you'd expect, as the septic system's located further away, it takes a lot longer for it to kind of discharge to the up to 10 years. So again, indicating long legacy effects from the contamination issue. So even if they make a change now, it's going to take a long time for this problem to go away. And also it means that when you've got these long travel times, that can be beneficial because you can have attenuation of the nitrogen as it moves through the system by processes like denitrification. But we still need kind of more data on the geochemistry in this groundwater system to kind of get an understanding of how much nitrogen attenuation may be happening in the groundwater before it discharges into the lagoon. We also looked at like how the exit concentrations will change as the septic system distance from the lagoon increases. And as you'd expect, you're getting less dilution of the nitrogen in the aquifer for when you've got the infrastructure located close, the septic system's located close to the lagoon. So finally, we ran simulations where we had multiple septic systems located all the way along the transect, where you've got kind of so they kind of aligned with where the households are. And interesting, what we found is a very large nitrogen plume that kind of slowly makes its way towards the lagoon. And so this was really important for trying to inform our future field investigations in terms of what kind of nitrogen levels we'd expect and where that nitrogen would be located. And overall, there was some variability when we ran simulations, including tides and variable recharge, but overall, the more simplified model was able to kind of replicate the overall behavior of the nitrogen moving from these septic systems into the lagoon. So it's just looking at the exit concentrations, which were generally similar for the different cases. So just in terms of kind of the preliminary, so this study is still ongoing, but generally in terms of our preliminary findings, we found that atoll hydrogeology compared to mainland hydrogeology leads to very distinct nitrogen discharge pathways between an inland source such as a septic system and the pathway towards the lagoon. We found that groundwater models, depending on what the objective is, should consider the ocean dynamics, including tides, in simulating these kind of contaminant transport processes in the atoll islands, because the groundwater system is very closely connected to the ocean around the island. And that these simulations, the results of them, they provide new insights into the nitrogen behaviour to inform future field investigations, so where they should target field monitoring and the installation of groundwater wells, which is costly, particularly in these remote areas, and shows the need to prioritise upgrades for the septic systems, particularly those that are located closest to the lagoon. So with that, and so the kind of next steps of the project are really the stakeholder involvement, which has been driven by the Pacific community group that we've been working with. And then we hope to kind of be involved with the field surveys as well as field monitoring to look at the nutrient and the nitrogen in the groundwater and its kind of transport pathways into the lagoon. So with that, I'll wrap up and just like to acknowledge, I guess the different funding sources and people that have helped contribute to this work. And so with that, I'm happy to answer any questions that anyone has.